Welcome back. Before starting the analysis in R, take a look at the final table with the coded factors and check if it matches with your table. If yes, let's change to R and start with the analysis. Let's start our analysis by loading the CSV data. In the data file, we have the coded variables xt, xp, and xc, the natural variables t, p, and c, and the response variable y. The next step is to run the data structure to check if all variables are numeric. In the data structure, we see that we have 12 observations of 7 variables, and all variables are numeric, so we are good to run the regression model. Let's start by running the complete regression model, the main factors, the two-factor interactions, and the three-factor interaction. The results of the complete linear model show that the p-value for the three-factor interaction is very high, 0.65, meaning that it is clearly not significant. So you are safe to run the model for the main factors and two-factor interactions, and that's what we are going to do next. We just need to replace this 3 by a 2. And now we have the model with the main factors and two-factor interactions. Let's run it. The result shows that the intercept xt and xp are significant, while xc and the two-factor interactions are not. We are going to start now a backwards elimination by removing one by one the factors and interactions that are not significant, always eliminating the less significant one. In this model, the interaction xp-xc is the one that has the highest p-value, 0.63. We are going to remove it from the regression model. To run the regression model without the interaction xp-xc, we just need to add minus xp-xc to the previous model. This way, we have the whole model for the main factors and two-factor interactions minus xp-xc. The linear model results show that xt-xc is the one with the highest p-value, the lowest significance, so we are going to remove it from the model. Now we have that the two-factor interaction xt-xp is the term with the lowest significance. So we are going to run the model only for the main factors xt, xp, and xc. Let's clean the code for the model with only main factors and run it. The model for the main factors shows that xt and xp are significant and xc is not, so we are going to eliminate xc from the model. Now that we finally have only significant factors in our model, let's take a break in the analysis to compare the several models we ran. The table shows the 6 models and some information about them: the number of parameters p, the r squared, the adjusted r squared, and the p-value. We can see that the r squared increases with the number of parameters in the model, and this behavior is entirely expected. As we increase the number of parameters in the model, the r squared is always likely to increase. However, if we look carefully, we will notice that the difference is small. The terms beta 0 plus beta 1x1 plus beta 2x2 present in both models are responsible for explaining 91% of the data variability. In comparison, the remaining terms are responsible for only 2.7% of the variability, the difference between the R-squares. That's why these coefficients are not significant in the t-test. This way, the R-squared is not a good indicator for choosing the best model. So other parameters are usually used to select the regression model: the adjusted R-squared and the p-value of the model. The adjusted R-square is in the linear model's output in R. It depends on the R-square, the number of experimental observations, and the number of parameters in the model. Unlike the R-squared, the adjusted R-squared increases as we eliminate the parameters with low significance from the model. In this table, the simplified model is the one with the highest adjusted R-squared. The same goes for the regression model's p-value. The simplified model is the one with the highest significance, the lowest p-value. Let's now go back to RStudio and run the natural model and the residuals plots. Let's start by running the natural model. Besides having different regression coefficients, the model statistics are similar. Both coded and the natural models present the same R-squared, adjusted R-squared, and p-value. The next step is to verify the residuals. So let's run the residuals plots. We are going to run with the experimental results, with the predicted results, with xt, and with xp. So let's run them. We can see that all the residuals plots with the predicted and experimental responses, as well as with the regression variables, are completely random distributed. Finally, we can run the contour plot of the yield with the temperature and pressure. The contour plot and the regression coefficients for the coded model show that the yield increases with both the pressure and the temperature, and the pressure has a stronger effect on the yield than the temperature. In these lessons, we have learned about regression models and how to use them to analyze experiments with inaccurate levels in the design factors. We have also looked in the statistics of the regression models and which parameters to take into account when choosing the most suitable model. I hope you have found it useful. Take care, and I see you in our next lessons.